Any questions on this? So this is just using the extra acts we're getting in to declare a packet as being lost or not. Okay, so what we're going to do with this is now decide when we make this decision that a packet was lost, how do we respond to it? Okay. The thing we want to do is resend the packet that was that we believe was lost. But as we'll see, this can be a little tricky. So let's walk through that. So response to loss, so far we've said on timeout, always retransmit the corresponding packet. Okay. What about when ACK-based rule fires? Okay. So what we've seen so far is that when we have this, so 3 subsequent packets that have been ACK event occur, you will retransmit the packet that you think is missing. Right? With individual ACKs or with full information ACKs, which packet you should retransmit is very clear. The whole is very clear in the stream of ACKs that you got. With cumulative ACKs, if you have a single packet loss, it's very clear. But what we're going to see is that when you have multiple packet losses, it's sometimes not clear. I have a detailed example in the backup that we'll walk through if we have the time. But otherwise, I hope you can see the intuition here, which is I received duplicate ACKs, but I didn't actually know which packets were received at the receiver. And so I'm going to have to guess when I retransmit a packet. Okay. So the response with cumulative ACKs issue, they don't tell the sender exactly which packets were received. They do tell you how many packets were received. That's the number of duplicate ACKs, not which ones to resend. And so that leads to some amount of guesswork around which one you should retransmit. And when we do TCP, we'll talk about how TCP does this in detail. Okay. Let's come back to this if people want to actually walk through the example. But for now, let's back up a level first and just taking stock of what we've done in terms of design building blocks. We have all of the design building blocks that we need to implement a reliable transport protocol. Checksums, ACKs, NACKs, timeouts, retransmissions, sequence numbers, and windows. There are trade-offs in how you apply them, whether you have cumulative ACKs versus full information and so on. But what you can do now is take all of those design options and design a reliability protocol. Okay, we've seen one, stop and wait. That was the one packet at a time. There's another very simple variant called go back n that you'll see in section. It's another one of these canonical examples, not very useful in practice. TCP is the one we will do in depth next time. But I think it's more important that you can reason about how to design a good reliability protocol from these building blocks, because in fact, as you'll see, TCP is not a perfect protocol in how it combines these building blocks. It's starting with the fact that it does cumulative ACKs. So we can do better, and we'll do better. Just a quick preview of what TCP does. It actually uses all of these building blocks, most of them that we've covered. It does use checksums, uses ACKs, no NACKs, it has windows, sequence numbers, cumulative ACKs, and it counts the number of duplicate ACKs. It does optionally have this option for a form of full information ACKs that we call selective acknowledgements, so we'll cover that as well. And then it has these timer estimation algorithms. Let me jump, I'm going to skip this for today. Let me jump to an example of ambiguity with cumulative ACKs. How many of you feel like you want to see the example? All right. So let's see where the issue comes from. So let's first look at responses with individual ACKs. Okay? The example we're going to consider here is a sender that has a window size of 6. And we're using a value of k equal to 3, meaning when I get 3 subsequent ACKs, not the packet I expected, I'm going to declare the packet as lost. Okay? So in this example, packets 1 and 2 have been sent and ACKed. 3 to 8 are in flight. So what I'm showing you here with these numbers are the sender's view of the window. Okay? Red are the packets that it has sent, but they've not yet been acknowledged. And you can have up to 6 of them, because that's your window size. And now let's say that you had 2 packets that were dropped, 3 and 5. Okay? So now what happens at the sender? When ACK 4 arrives, right, what is the sender going to do? It's going to say, okay, packet 4 was delivered, I have a window size of 6, so I can now send packet number 9. When ACK 6 arrives, it says, okay, packet 6 arrived. I'm allowed to have 6 in-flight packets, so I'm going to send out 10. Are we good with that? Now when the 7th ACK arrives, this is the 3rd subsequent ACK. So the sender is going to say, okay, packet 3 is lost, because I've gotten 3 acknowledgements after 3 without receiving 3. So packet 3 is gone, so that means I can resend 3. Plus I received an ACK for 7, so I can send one more packet, so I can send 11. Is everyone good with this step? Yep.
It's not a real window on the packet sequence, it's a window on the queue of packets.
It's a window in the sense of how many outstanding packets can you have. Yeah. Are you good with that? So when we do TCP, we'll do the actual how you maintain the variables and what range of windows you can have outstanding. But for now, it's 6 packets in flight. Yeah. So what happens when ACK 8 arrives? So at this point, you've gotten 3 subsequent acknowledgements for packet 5, right? You've gotten the ACK for 6, for 7, and for 8. So you're going to declare at this point packet 5 is lost. So you're going to resend 5, and you get to send 12. Is everyone comfortable with why I get to send 2 packets? Yeah, okay, great. And then when 9 arrives, you continue, you send 13 and so on. So this is pretty clean. If I did the same example with full information ACKs, it would look exactly the same because you're getting the same information. Okay, so we're going to skip it, but walk through it in your heads. So now let's walk through this with cumulative ACKs. Okay. So when you get the ACK corresponding to packet 4, what you receive at the sender is something that says, I'm acknowledging 2. Okay. So this is our first duplicate ACK. But I did get 1 packet out of the network, so I get to send 1 more, so I send 9. When I get the ACK for packet 6, it is still saying acknowledgement 2. The number of duplicate ACKs I now have is 2. Okay. So I'm going to send 10. Everyone good with it so far? Right. When I get the acknowledgement corresponding to packet number 7 now, so at this point I have 3 duplicate ACKs. So this is the point at which I decide packet 3 is lost. And it's clear which one is lost, right? Because I've gotten everything up to 2. The reason that number is not going up is because 3 is lost. So I'm going to resend 3 and send 11, similar to individual ACKs. Are we good so far? Yeah. So where the trouble occurs is when you get the next ACK 2. So when corresponding to packet 8 being received, you get yet another ACK 2. And at this point, you have 4 duplicate ACKs, so you know that there's a packet that got 3 subsequent ACKs. You know that since a packet was received, you're allowed to send 12. But which packet should you resend? You have no way of knowing whether you should resend 4 or you should resend 5 or some other packet. Is this making sense? Okay, and so when we talk about TCP, we'll talk about how TCP addresses this, but this is the problem that is being addressed. And since I have 2 minutes more, let me go back in time and cover one other thing. So everything we've been talking about so far is reliability based on this notion of I'm going to send a packet, wait for acknowledgements, send another packet. So it's ACK based. Any other thoughts on how else could you do reliability? If I didn't want to do this per packet accounting or just a completely different design approach. Clear your heads of everything we've talked about this. Yep. You're on the right track. So you could just send packets, keep sending packets until the receiver tells you, I got everything, stop. And you mean keep sending the same packets over and over. Could you do better than that? So if I had 10 packets to send, I could just keep sending 1 to 10, 1 to 10, 1 to 10 until the receiver tells me I got all 10. Valid. It's a totally valid reliability protocol. It's not very efficient.
Would you implement like another protocol? Like, okay, so if you don't receive like an acknowledgement for 3, the sender like probe and be like, hey, did you receive this packet and ask for an acknowledgement?
So have the receiver tell you which packets it wants.
Yeah.
Yes, that would be a little bit of a pull-based. We're kind of using ACKs to do that. Right. For those of you who've maybe taken some EE courses, what we could do is use coding theory, and there is a large amount of work in this space, which is you take the data and you encode it to be resilient to loss. So the way this works is you take, say, k packets, you encode them as some number of packets n larger than k. So let's say you took 4 packets and you could encode it as 7 packets. And these codes have a property where it says you took 4 packets and you encoded them as 7 packets. If you receive any 5 of these packets, I'm making up numbers, but if you received any 5 of these packets, you would be able to reconstruct those 4 packets. So there is this entire literature on different coding schemes you can use that would allow you to tolerate some amount of loss, but still not, send every packet 10 times. So you could just keep sending packets with some amount of redundancy built into the packet. And you can reconstruct the original packets from the encoded streams. So there's a whole literature on codes that have very different efficiency trade-offs. We don't cover them in this class. I just wanted you to know that coding theory and coding packets is a reasonable approach to doing reliability. It's not commonly used on the internet. Some of the video streaming protocols have used this at the application layer, but it's not made it to one of the internet's transport layer protocols. But it is an option if you wanted to do a slightly different form of reliability. The benefit here is that you don't have this back and forth on acknowledgements. You can just send a stream of packets, and it's tolerant to a certain level of loss. So with that, any questions? Okay, thanks. Next lecture is a review lecture, midterm review lecture. Thank you. Oh shoot, this was off the entire time.